Good morning. Good morning, everyone. I'm putting a link in the chat where you can select your sign-in sheet and fill it out. Welcome to the Interactions PD, where you're going to learn about Unit 1 and the overview of the curriculum. We'll officially start in about 1 minute. I see one participant has joined the trail guide.
Raining.
Morning. So row 1 on the trail guide is the sign-in sheet. Let me know if you have any difficulties joining. I'll be muting your microphones until the discussion time, unless you have a pressing matter.
And the younger generation just isn't sticking around. They're not the jobs there. The factories are gone.
So I'm going to go ahead and mute Scott and Miss Danyan or Margarita. Hi, good to see you again. All right, it's 8:31. Let's go ahead and begin. I'm gonna admit one more participant. Welcome, Judith. All right, good morning, everyone. My name is Michael Lim. I'm going to be your facilitator for today. I'm a teacher at Gardena High School. The next time you have a PD with interactions is with Adam Paskowitz. He's from Narbonne High School, so you'll meet him at that time. So go ahead and sign in. Let's see how many participants in the trail. Good, we have 5 participants now in the trail guide. So go to row 1 and sign in. Have another participant joining us. Good morning, Josephine. Oh, we're having some unexpected guests, so we'll continue to let participants in. I had 5 reserved. We're going up to 7 now. Good thing I didn't have to make photocopies. Welcome. Welcome to the Interactions PD. Please sign in on the Trail Guide row 1. So there's a new policy with Zoom PDs in LAUSD. All cameras must be on, and it cannot be from a cell phone anymore. So if you're driving from one destination to another, the compensation will not be provided if it is not on a computer. But it looks like all of you are stationary, safe at home. Here are norms to ask questions, preferably in the chat, or you can unmute your mic if it's a
Morning.
Good morning. So you can unmute your mic if you have a pressing matter. Try to integrate new information, have an open mind, utilize what you learn, and monitor your own devices. Speaking of monitoring needs, let's go ahead and click on the agenda in row 3 of the trail guide. The agenda will show you the breakdown of today's PD. So 8:30 is the welcome and inclusion, 8:35. I sent out a survey to those who reserved the spot in this PD today. Those who are last minute joining, sorry you didn't get to fill out the survey, but that's okay. You'll still see a few responses of what was the most challenging or pressing matter in your school year. 8:45, we'll do the interactions overview. 9 o'clock, interactions resources. 8:45, excuse me, I should say 9:15. With a unit overview. 9:20 will be investigation 1. And 9:30 will be Google Drawings, talk moves, and investigation 2. So your first bathroom breaks can be at 10:15. We're doing a 4-hour session today. There won't be a lunch break, but there will be a 10-minute bathroom stretch break in about an hour and 40 minutes. Then we'll move on to investigation 3. We will learn about how to do claim evidence reasoning. At 10:40, we'll do some reflection and planning, then cover investigation 4, have a group discussion. And the second reflection and planning, I'm actually going to edit that. 5-minute break at 11:30, more PD, and then at 12:30, we'll have an adjourned meeting. So packed schedule. Let's go ahead and get moving to the objectives. So day 1's objectives is to understand the purpose of interactions, how to access materials, understand the scope and sequence, understand the storyline, acquires teaching strategies, and to reflect and plan on past and upcoming interaction activities. It's already the month of October, so you're probably already knee deep into the curriculum, but we can still reflect on what your results could mean to you, how useful they can be, or what your planning could look like going forward. Agenda. And now here's our inclusion question. So my wife is a English teacher. She was a high school English teacher for 8 years, and now she's a consultant for college application essays. And she came across this article that what if people used not to-do lists? There's to-do lists and not to-do lists. So what I mean by a not to-do list is what's a task or a chore that could be draining or demotivating from your teaching? Let me show you an example. I'll put the link in the chat. So this is the not to do list. So if you go to the chat, click on that link. What's something that would drain your energy instead of give you energy as a teacher? And I started to think about the food that I eat. And this is something I eat for my birthday, around month of April. It's a meat lover stuffed crust pizza. And it is something that tastes delicious and is amazing at the moment. But then the next day, I feel so tired. I feel so um, unhealthy, maybe a little bit of shame, and it just takes away from my teaching instruction. So I'd love for everyone to put in the chat what's something that I could add to this list that we can try to avoid as teachers. And the more specific, the more powerful this inclusion activity can be. So maybe it's a food, maybe it's a bedtime, it could be uh, a TV show, or what's something that could take away your energy as a teacher, like a specific task. So if everyone can participate, that'd be wonderful. Um, if not, okay, there we go. So staying up too late. So that could be a task that we avoid if we are more mindful with our time. Thank you, Mina. Anyone else? There's 6 more participants in this room that could join in. Cooking. So cooking can also take away from our energy if it takes a long time. Maybe you have to grocery shop. Maybe you have to clean up. I mean, I'm sure there are some teachers out there that would love to do cooking and that would energize them. But specifically for Miss Afonta, cooking is something she would prefer to avoid. Not having enough sleep. Right. Responding to a constant barrage of emails. All right. Thank you all for sharing. So, not to-do list. This is something you might want to use um, this week, this coming week. So when I sent out the question that stated, oh, we have one more, unclear expectations of admin. Add 2 more, responding to every negative talk. Great, thank you. Welcome back, Judith and Josephine. Thank you for your not to-do list task. So 3 concerns were emailed, were entered into the survey, and one was lack of previous background knowledge. So as an interactions teacher, maybe it's not what you're certified to teach at this moment. Maybe it's a last minute assignment from your admin. So what can a teacher do to learn about the interactions curriculum if there's a lack of previous background? So this link is in our trail guide. It's row 5. So if everyone can go to row 5 of our trail guide, you'll see that there is a cheat sheet for the interactions curriculum. You can see a little bit of background information of each unit, the guiding questions, anchoring phenomena, the standards, and the units again in that order: guiding questions, anchoring phenomena, and the standards. If it's your first time teaching interactions, you'll see that there is I'm going to use the word storyline, which is there's a beginning, middle, and end to a process. And the beginning of interactions is about helping students see, and for yourself, if it's your first time teaching it, that atoms make up all things, and atoms are held together by opposite charges called protons and electrons. And those atoms can cause properties, certain specific properties to manifest. So if you have pi pans on a Van der Graaf machine, those pi pans can repel if those atoms are charged. If you have two pieces of tape that attract one another, those will attract as opposite charges, but if they repel, it's because of similar charges. And if you extend this concept to everyday phenomena, lightning strikes occur because of similar charges between the electrons in our air. And clouds can generate charge because the atoms are colliding into one another, transferring that electron charge. So in Unit 1, students are learning that there is a big science idea called the atom, and the atom is held together by opposite charges. In Unit 2, the interactions curriculum will extend this topic or build upon this topic of atoms to chemical bonding. Why do things explode? Well, how does a small spark cause a huge explosion? It's the atoms that we learned in Unit 1 being close enough to attract, but not too close to the point that they repel. And there's a balance of attraction and repulsion where a chemical bond forms. And when that chemical bond forms between two atoms, energy is released as an explosion. So students build upon atoms, the concept of chemical bonding, and the conversion of energy. And then in Unit 3, the students learn that there are molecules that attract other molecules. So groups of atoms attracting or repelling other groups of atoms can cause a hurricane through the transfer of energy when water molecules condense. So the phenomena gets bigger and bigger, right? You're going from pie pans to scotch tape to lightning, but then you go to explosions to hurricanes, all connected. And the students use the same language. They refer to the same evidence that they acquire and procure from each daily activity. And the last unit, after they learn to explain hurricanes through the attraction and repulsion of molecules, they start to focus inward that fevers can be deadly at a temperature of 107 degrees. So the atoms from Unit 1, the chemical bonds in Unit 2, the intermolecular forces in Unit 3 all coalesce to explain proteins. Every human being uses proteins to fight disease, specifically the antibodies. And these antibodies are held together by intermolecular forces, which are held together by chemical bonds, which are held together by atoms. And those proteins can unravel when there is a hot temperature, like a fever. And once that temperature of 107 degrees is reached, the protein can no longer do its function, such as fight disease. And now a human being will be extremely vulnerable to viruses and infections and other foreign elements, and the person will cease to live. So the storyline is continuous, it's coherent. Students will know why they're doing what they're doing in your class because of the the phenomena. So that is the benefit of this cheat sheet. Another way you can acquire more background information of teaching interactions is to watch the video recordings that Adam and I have facilitated for other participants. And that's going to be in the trail guide, row 7. So if you go to row 7 in the trail guide, you'll see that there is a website that will contain all the links to all the recordings. So yes, today's actually being recorded also, or it was. Let me see if I can. Yes, it is recording. And I will post this PD on this website also. It's for LAUSD interaction teachers exclusively. But you can see that back in 2022 and even 2023, the Zoom PDs of similar or exact topics as we are discussing today were recorded, and resources are connected to those recordings. So if you're a new teacher or you need a refresher, or you even just want to prepare for the next day or week or month, you can just rewatch these video recordings, go through these slide decks, and get an overview of what your classroom should look like. So that is another resource. Let's go to row 6 and make sure you know about our newest resource. So everyone look at row 6 in the trail guide, and you will see that there is it's my slides. Let's see if I get used to 2. There we go. Row 6. Schoology course. It's called Teaching Interactions. If you go to Schoology and you type in the access code, here, let's go ahead and copy this. You're going to access our latest resource. So I'm going to go to Schoology. I'm going to go to courses and then click on my courses, join a course, and then put in the access code. So I just copy pasted it from the trail guide. So when you click that, you should be able to join the interactions asynchronous PD. And this was designed for teachers who have never taught interactions. There's an introductory video, and you are supposed to be compensated up to 12 hours at your hourly rate, depending on your school site administrator. So originally, we wanted the Division of Instruction to help pay for the compensation of this online course for new interaction teachers, but the funding is no longer available, so it now moves to the school site. Each folder will provide a teacher with how to start from ground zero, what's the course overview, the purpose, introduction to the course, similar resources to what we're covering today, and also the curriculum. So each folder is going to have a list of exercises and tasks, kind of like scavenger hunts. There's going to be videos. So Margaret is asking, I'm already in the Interaction Teachers group. So this website that's on my screen is for the course for brand new interaction teachers who need to learn from the ground zero, because 4 hours is not enough. Even though we're meeting from 8:30 to 12:30, it's not enough scaffolding. It's not enough introduction. We don't get specific enough. Okay, so the request has to be accepted. Let's go to my notifications. There's a request, and it should be showing up. There you go. Scott is granted access. Welcome to the asynchronous course. So this will all be, it should take about 12 hours to complete. And your administrator should be compelled to pay you the 12 hours because you get a certificate and the administrator will actually be relieved that you're receiving more and more support for this. Miss Agassi says I can't join. So Mina, did you go to courses
Yeah.
and
So I
courses?
copied the um that code from
Oh,
the
okay.
thing and I pasted it in that and I went to courses.
Okay.
It's that two C8H one, right?
Let me go to the trail guide. Trail guides.
Maybe I can't copy and paste. Maybe I have to type it in. Hold
It's
on.
J4ZG 2633 SPW. So that's the one you copied and pasted, Mina?
I don't know.
Six?
Maybe I'm looking at the wrong thing.
Yeah, if you go to the trail guide, row 6, we'll have the
Oh, sorry. Okay.
row
I was
6.
copying the wrong one. Thanks.
It can get really confusing because there's groups and then there's courses and then there's access codes and um, other things that could just really get confusing. So no problem. So try to join, and then that is something you can do after this PD or in the next couple weeks, and then ask your administrator for the compensation. Okay, so that addresses our first challenge or need, the background information. Next is, oh, oops. Okay, let's see if I can put this back. Next is, I'm a co-teacher with an ELA social science background. The interactions curriculum is organized significantly differently. I have wonderings about content and assessment. I understand interactions, activities, modeling phenomena, etc., but I'm curious as to what assessments and directed instructions for interactions may look like. Great question. Assessments are a snapshot of what your students should be able to do by the end of the semester or school year. Our trail guide has row 8, 9, and 10 assessments that I have made personally for my students. So they're kind of like unofficial assessments if you don't want to go the multiple choice question route and the open-ended response route. But if we click through these together, you'll see that each assessment that I have for units 1, 2, and 4, I've actually never taught unit 3 because of my block scheduling at my school or other projects that my school has assigned to me, like linked learning or CTE pathway projects. So those have kind of taken the place of my unit 3. But unit 1, 2, and 4 are available. So at the end of the semester, students should be able to draw this final model. Please don't share it with students. And I'll show you how to make this template. But they're going to explain why a PyPan will repel off a Van der Graaf generator. The second assessment is unit 2, where students explain why a balloon of hydrogen and oxygen gas explodes. It's the formation of water molecules. And I also have a template to provide for you also later today. And then this last one is the unit 4 assessment, where students are explaining why a fever is deadly. And I will provide that answer key at the end of our PD. But pretty much it is a antibody that is produced in the human bloodstream that will change shape because of the fever, and that shape will no longer fit a virus to break down the virus, and then that virus will multiply and kill the patient. But the temperature will rise in the fever, causing the deformation of the protein, and also the ability to survive will also decrease with each raising temperature. So those are some assessments. Here's a rubric for that unit 4 model. So macromolecules, polar, nonpolar, intermolecular forces, temperature, and connections. So that is something I want to provide as assessments. Now, if you want to go the more traditional route of assessments, it's going to be in our interactions Google site. So this one,
Is that where the tasks are like labeled like 1.1.3, 1.1.4?
so are you referring to something I shared earlier today? Or
No, I'm thinking that the more traditional route is like the one where it has like multiple choice questions or short answer, and there's like videos that the students can watch, like with the Van de Graaff generator.
yes.
Okay.
So this link is the traditional assessments that was authored by the original writers of Interactions. So if you click on that in the chat, Scott was alluding to multiple choice questions and open-ended responses. So each of these unit tests, or part 1 or part 2 unit tests, will take you directly to the multiple choice questions with open-ended responses. Now, the reason why I created my own is because of the time it takes. Whenever I taught interactions, it was always classes of 36 students or more and multiple classes. So multiple choice questions, super easy to grade. But when it comes to open-ended responses, you have these students that might have a literacy level that causes a lot of struggle to decipher, to reread, and it is very time consuming. So there are more traditional questions, and I actually haven't used these in such a long time. I don't think there are multiple choice options here. Let's go to preview, and I think they're all open-ended. I've taught interactions for almost 8 years. A lot of those are just interaction lessons embedded in my chemistry classes. I've taught 17 years of chemistry in LAUSD, and I started picking up on interaction lessons 2015 and on. So I remember administering this exam, and they are all open-ended responses. But there are videos, there's models that students will draw, and there's phenomena that you can actually, if you choose not to use their traditional assessments, you can actually just use these videos as alternate phenomena in your classroom, or alternate assessment questions. So don't use the whole test, but just use several of the robust questions as one test question, or make that like a quiz if you want. So does everyone have access to the what is this, 6 links on my screen? If not, let me know. There is a Schoology group. Okay, let me read the chat here. I'm unable to view the models at the moment. Is there any way you can share screen? So Scott, I did have them on the screen, so maybe I answered that question. All right. So if no one has any issues accessing these traditional exams, we'll move forward to the next challenge. Oh, direct instruction. So direct instruction is supposed to be a lot of talk moves. Let me explain. So I'll put in the chat. Direct instruction. So there's a link that'll take you back to that website, but to a different page. And as a science teacher, I always lectured. It was a 5-minute, 10-minute, 20-minute lecture where students had to either fill in the blank or just take notes on a piece of paper. Interactions does not have lectures. Interactions has discussions and hands-on activities. And if you click on this thumbnail, you'll see that there is guidelines of how to do the discussions. There's going to be goals for productive talk, and that is to do all of those tasks that you see there on your screen. So I'm going to put this on my second monitor so I can see better. I have my second monitor projected on my curtains in my living room. So I'm looking at curtains right now when I look up, but when I look down, I can see the screen in more clarity. Okay, so the goals for discussion, you give them time to think, of course, but instead of saying, that's the wrong answer. I don't think any teacher ever says that's, to a student as a response, that's the wrong answer, but to hint to them that they are completely inaccurate is what Interactions tries to shy away from. It's more about, can you tell me more about that? But you say it with a very stoic and unreadable face. Try to stay as unreadable and neutral as possible, because whenever our facial expressions or our tone inflections hint that a student is correct or a student is wrong, then the discussion becomes more about guessing what's on the teacher's mind instead of what is really true. And so I'll give you an example. One of the hands-on activities of Interactions is to explain, well, is to first separate Scotch tape and to demonstrate the attraction between the two strips. And when students are asked, why does this happen? Or can you explain why it does that? And they say, it's sticky. The tape is sticky. As a teacher, my response would be, can you tell me more about why things attract? Because when students are asked a more specific question or a clarifying question, they start to narrow their focus, and then they can actually respond using the science ideas from the activity. So if a student is responding, tape attracts because it's sticky, and you respond with, why do things attract? Their mind is now focusing on the opposite charges that tape has. And if the student says, oh, they have opposite charges, then you can ask them, well, where have we seen that before? Or can you give me an example? I'm going to open a slideshow since we're on this topic. There is, okay, in row 30, there is a slideshow. Let's try this one. So this is something pulled from my chemistry class, and I'll show you how I integrate the, let's make sure everyone has access. Let's go to share. Yeah, anyone with link. So I'm in row 30 of the trail guide. And if you actually can just look at the screen, you don't have to go to this.
I have a quick question.
Yes.
So like so I'm a co-teacher. So my co-teacher, we did do like an activity where they observe a phenomena, for example, like the Van de Graaff generator.
Yes.
We also did the tape phenomena. So my question is, like, for students who most of them are not going to be able to produce like content diction, like positive charge, negative charge, balanced, neutral, electrostatic. So they can say things like the tape is sticky or they stick together because they're sticky. But like, I guess my question, because by the end of the task, we're hoping that they are describing the phenomena with that scientific diction, I'm assuming.
Yes.
So then my question is, like, from when they observe the phenomena, but they don't have the language, to when they do some type of assessment, and the assessment, at least that I saw, does require them in their short answers to use that type of diction or that type of content language. Like, when would they have gotten the explanation of like, this is a positive, what a positive charge is, this is what a negative charge is, this is what neutral
Yes.
means, this is what electrostatic. Because in the beginning, they don't have that language. They're just observing
Yes.
and they're kind of talking it out, which I get. But then, like by the
Absolutely.
assessment, they need that language to describe what they're seeing. I'm trying to bridge like where between those two activities do they
Of
learn
course.
the content if they don't have it from when they're just talking about it and they need it when they're going to get assessed on it.
Of course. Yes, we shouldn't expect students to know something that they were never taught. And if you're ever in a situation where students are extremely limited in their prior knowledge, whether we didn't teach it or their previous class didn't teach it, then the safest route to go to keep the student's mind open is we can say, what does this remind you of? Or have you seen something like this before? A lot of students have seen balloons rubbed on hair that will attract between the two, or if they have ever rubbed their feet on carpet or tile with socks on and they shock somebody, like they have little experiences that could help them connect what they just did to their prior knowledge. And in that same activity of the Scotch tape, there is a simulation that would be a great support for these students who don't know about positive and negative. So I'm going to show you this simulation. Let me get to the two spheres and the charge within the spheres. So right here. So when I show this slide, and if you want to follow along, it's in the trail guide slide. It's hard to read. The curtain, slide 52. Or you can just look at my screen. When students see that there are objects that could repel or push away, or objects that could attract based on a combination of symbols, there you start to build the bridge. Oh, things come together because according to this picture, they're oppositely charged. Things will push away because they are similarly charged. And if they still don't make the connection, you can walk right up to the screen and then just gesture to all three boxes. And if they still look at you with a blank face, you could ask someone what do they know is the cause. So that's the benefit of having, a large group. I don't know if all of you have classes of 10 or more students. Maybe in the chat, could everyone just put in a number, how many interaction students you have in your class, and then we could work from there. When I teach interactions, I have students do the hands-on activity and watch a video of the hands-on activity to make sure they have the same results. And then I like to show these images called GIFs, and I'll show you how to make them at the end of this, towards session 3 of this PD, to have students revisit and to review the concepts that were covered. Because on my other slides, I have the Scotch tape activity. So even students who are absent, or students who don't pay attention, or students who are on their phones, when they have the phenomena displayed to them again and again, they start to feel like, oh, I know what's happening in this class. And the top tapes and the bottom tapes, like this top square, is just like this bottom image in Mr. Lim's slide. So opposites attract. And then the two top tapes and the two bottom tapes, they act like the two images in Mr. Lim's top slide, in the top of his slide. So you've got this layer of support where spheres can mirror the Scotch tape and you discuss it. It's good to have a rule of 3. You have one student say what's really happening, a very accurate explanation. You have a second student paraphrase that. And then the third student could either add or paraphrase to that also. And usually, I don't have students that give complete answers, complete accurate explanations. They'll say bits and pieces, and then you call the second student to add to those bits and pieces, and then maybe you have the third student paraphrase. But once you get 3 students to voice their ideas and their connections, your class starts to see, okay, Mr. Lim's going to do this thing of 3. And so I get 3 chances to hear what I'm curious about. I'm wondering, because he's not telling me why the Scotch tapes attract and the Scotch tapes repel. He's not telling me. He's withholding this information because he wants the students to explain. And that's why the talk moves are so valuable. This will take a lot of patience, and it will take a lot of adjustment if you are doing a lot of lecture. I see Judith has a class of 20, so it's perfect for the students to hear from one another. If you have access to Nearpod, you can have students pair share by posting a Nearpod question, and then they type their partner's response, and then they will share out loud 3 times. If you have a smaller class, then you can actually just do a round robin and have each student go around and share one idea, bits and pieces, fragments of evidence, inklings of ideas. All these different ways of sharing is the way interactions is designed to be instructed. Now, of course, you can go rogue and do lectures if you like, but you'll find that you'll run out of content very quickly if you keep telling students what to think and what to memorize. So that's the direct instruction. If you want to see video clips, video recordings of live instruction, then the link in the chat. Oh, we already have that open. Has video recordings of the teacher. So here's one on the pie pans in Van der Graaf. Here is one on the, let's see, investigation. This is about cutting paper. This activity is on the alcohol and water mixtures. This activity is on the simulations of the atom. And this is the same day. So these 2 videos are the same lesson. And then this activity is models. Students will draw models. So Scott asked the question, what do we do if students don't know what to say because they haven't been taught it? Well, you have the simulations in the curriculum, but also students will draw their best guess on a piece of paper or digitally. Hopefully, your students have Chromebooks. Now, models are so powerful because it's the student language that is universal, right? ELs, special needs, GATE students, and just your average Joe Schmo student. You've got students taking their best guess, and then you select 2 models that show strengths of one part of the explanation and strengths of the other part of the explanation. And once you procure these models from your student submissions, you can just reuse them every year. You don't have to keep trying to vet, oh, this particular class made this model and this class made the other model, and now I have to use 2 new models and try to facilitate a discussion. What's the strength and weaknesses? So the pie pan and Van der Graaf models These were drawn by students, and they both have strengths and weaknesses. So what's very useful and valuable about showing two models that have strengths and weaknesses that are not the same is there's a debate. When students say, I think student A's model's better, and most of them will say, and if you ask them why, and they'll say, because it has more detail. It's like, tell me more. Tell me about the charge. So students will observe that there are models that have positive charges next to positive charges and models that have opposite charges. Now, this model drawing happens after the Scotch tape activity. This model activity happens after the simulation of the two spheres that are positive, positive, negative, negative. So when you have students pair share and they say something like, oh, one has more detail, or they say something like, oh, student B is better because it has positive opposite charges, right? Those are very limited reasons, but they can build from that once you have the talk moves. So when you ask students, why do you think student A is better? And they say, oh, because it has more detail. And you say, okay, well, tell me about the charge. And they'll say, oh, they're all positive. And then you can say a follow-up question, what do positive and positive charges do? How do they interact? And if they freeze up, you go back to the slide of, well, look at these images. What do these images communicate to you? What have we learned from the Scotch tape activity? And then some will say, oh, because opposite charges repel. And then they can correct themselves automatically. Self-correction is probably one of the most powerful moments that these students will experience in a talk move. So similar charges repel. Student A's model is better. Student B's model is better. Maybe students will say, oh, it's better because it has positives and negatives. Then you ask them, well, what do positive and negative, what are they supposed to do? According to this image, opposites attract. If the pi pans repelled off the Van der Graaf generator, then the students should be able to say, okay, that's not the explanation of why it repelled. However, before the Van der Graaf generator repelled the pi pans, there were positives and negatives in all things because it was neutral. So you can use mine, you can use your own, you can use a mixture of both. The point is, interactions is not to be taught by lecture. It is to be taught by comparing resources, exploring phenomena digitally, but then also hands-on. And this leads me to the third concern of interaction teachers. One of you said, getting my students motivated and engaged is a challenge. I hear you. I am so with you. I have never had such unmotivated students in the past 17 years. These 10th graders seem to be a different generation than other 10th graders. And so I have some suggestions. When you have classes, okay, let's even narrow the focus down. If you have one student who seldom does his or her work, if you have small groups of students who seldom come to class, if you have large groups of students who are absent 10 or more times per quarter, okay, you will be exhausted. You will find you have very little to give to everybody. So this is what I recommend, and this has helped me so much for myself to stay motivated and for the students to stay motivated. Each day, you are trying to win over the student or small group of students or the large group of students. The same way we win over a significant other, a friend that we had an argument with, maybe even a boss, an administrator, maybe even a parent. How do we win over people? It becomes a people issue. And it's helped me. It's helped me as a teacher to realize, okay, I know what Dominique, I'm not going to say his last name. I know what resonates with him and what doesn't. And when I learned about that, I actually developed this arrangement with Dominique, right? He's going to be the student who passes papers out. He has to be the one, or not papers, but resources, whether it's collect cell phones and put them in yonder pouches, whether it's pass out materials for the hands-on activities, or to collect materials, or to drop off safety goggles. Once you find out what gets a student to either stay in his or her seat to start his or her activity, then you have to use that again and again. Maybe this is common sense to many of you, but it's so easy to forget and not make it common practice, because we work for a very special district and we may not get the support we need. We may not get the time we need. And we have to pivot. So focus on that one student that's unmotivated and prepare for that student that next day, or the small group or the large group. It's all about preparing each day for these different personalities, these different prior experiences, these different work habits, and to adjust and adjust. And maybe you don't get every single interaction students to be inspired and driven to go to college. It'd be wonderful if they could. And if they don't, you can still dangle the motivation that they can graduate high school by being in your class. And if that does not interest them, you still have the carrot to say, you can pass this class if you can do these hands-on activities and do these discussions and draw these models and show up and start the assignment and to go back to your seat, right? All these different challenges can be scaled. Go to college, graduate high school, pass the class, or even the bare bones, respect one another. Sometimes you just have to stop teaching and you just have to start interacting with the students in a way where you get their respect. Maybe you bend a few rules. You didn't hear that from me, but you need to make sure that the connection between the students and yourself is as real as it gets. And it might involve contacting parents and documenting your communications. My school has a lot of extra counselors because of different programs, such as BSAP. And then we have, I think, 4 PSWs. So Gardena High School is a priority school. So we have a village of counselors, getting them all involved with these unmotivated students and letting them know that you are not going to give up gets their respect. And once you reach that level of respect where they start responding, or they stop, doing disrespectful and inappropriate things, you will see the fruits of your labor, and they'll start learning, and they'll actually try to be a better person. So that's what I have to share about unmotivated and disengaged students. It's all about being that adult that demonstrates resilience and expertise, but also care, and even a daring perspective, being bold and learning to personalize your classroom. I think that's as far as I can go with a group recommendation. So please don't give up. And when students see you not giving up, then they at least learn, I can be as strong as this teacher and learn from my other classes, learn in life. Because Mr. Lim, he gets disrespected sometimes. Mr. Lim gets overwhelmed sometimes. But look, he's still doing his job. He's still doing his work. I can do my work, regardless what it is. All right, it's 9:27. It is time to go over the resources. So 2015 is when I started teaching interactions, and this large group of piloting teachers has narrowed down to you for PDs. If you teach interactions, students should develop a flexibility of thinking and a depth of thinking where they solve problems and they can make better decisions and they can innovate. And if they can make sense of the world in which they live, they can learn more if they need to learn more. When I taught chemistry before interactions, it was always finish the class, now either become a chemistry major or do physics. I didn't have this mindset that it's all about learning stuff. It's not really chemistry. You're just learning how to learn. And then once you do that, you can learn anything. And as an interaction teacher, it actually has helped me so much to learn better. Yes, you can read an article. Yes, you can memorize vocabulary. And yes, you can do practice problems. But to draw a picture that represents your thinking, as an interaction teacher, you should be drawing many, many models to the point where you can draw any explanation of any phenomena whenever you need to. And interactions is the only curriculum that does that. Other curriculum uses models already made or just refers to models as diagrams. They don't really explain, they just portray things from a bird's eye view or from a dissection, like as if something was like if a phenomenon had an autopsy, all you do is see what's inside. But the workings is rarely demonstrated in many science textbooks. So building your own models is a skill you'll learn, and students will learn that too. Interactions is a ninth grade. It's designed to be a ninth grade introductory physical science course. I've taught at 3 high schools in the past 17 years, all LAUSD, and they've used interactions as a remedial course. Students who failed chemistry and physics are to take interactions. Students who did poorly in middle school science are to take interactions first. So interactions may not be the way, it may not be designed for the purposes your school is using it, but this is the original vision. It's NGSS aligned. Most of the tasks that students will complete are models and explanation. This embodies the nature of science. Students are making sense of phenomena. Interactions only cover 7 NGSS standards. It doesn't cover 20 or more like the other course subjects. That's why it's an elective course. And all you need is a science credential of any type. So if you're a life science teacher and you ended up with interactions, you are qualified to teach interactions, but it won't be easy. This is not a substitute class. This provides a foundation, and there's no part 2 or 3 to this course. LAUSD adopted interactions because ICS was not NGSS. Interactions is, so we swapped the courses. Interactions has won an award called the Example of High Quality NGSS Design. This was awarded by the organization Achieve. And we already discussed some of the pedagogy of interactions. It's all about discussions, so students either realize their misconceptions at the time or they will self-correct their misconceptions later. The teachers should refrain from making corrections immediately. That way the students stay open-minded. Students figure out phenomena, there's academic discourse. Models and explanations are the final product of interactions. And the interactions curriculum is a storyline. It's a progression. They first learn about Scotch tape. They add that knowledge to Van de Graaff's pipe hands on a Van de Graaff generator. They apply that to a Franklin belt. They apply what they learn to a mixture of alcohol and water. All these connections, it's progressive. And the use of student artifacts, of course, cover the names, is a powerful discussion tool, but also, in a way, it's an informal assessment by having them choose which model is more accurate. So after this PD, maybe you think the interactions curriculum implementation will be a straight line, but it's not. In reality, you're going to hit many hills and valleys. And then that's why the PDs are offered by the Division of Instruction. Your next PD is going to be in January. It's going to be a hands-on, in-person PD at the high school, Eagle Rock High School. This is in January. And you'll be working with Adam, and you'll be doing Unit 1 and some of Unit 2 hands-on activities. And then in February, you're going to be doing the hands-on activities with me at Eagle Rock High School for Unit 2, Part 2, and Unit 3 and 4. And that'll be a 6-hour PD. And hopefully you'll get a very clear picture of what to do, what not to do, and how to do it. Go ahead and read over these driving questions. I'm going to get a sip of water. So what does a curriculum look like at 30,000 feet? There's 4 units, just like that slide demonstrated. But then within each unit, there are something called investigations. Investigations are bundles of lessons, but interactions doesn't call them lessons. They're called activities. So in Unit 1, there are 20 lessons. In Unit 2, there are 17. In Unit 3, 7, and Unit 4, 7 lessons. So a total of 49 lessons. If you lecture, you're going to go through these lessons so fast that you run out of things to teach. So that was another public service announcement. Don't lecture. It does seem easier, but you have to let the students process and communicate so it becomes part of their language when it comes to the charge or atoms or chemical bonds. So there's a pacing plan. I know it's a little late because we are already in October, but there is a pacing plan. I think it's in the trail guide. Let me go to my, close the talk moves. It's a slideshow. Slideshow, trail guide. We are looking for pacing plan. Okay, I have it in my slide, and I will put it in the chat. So if you click on that link in the chat, there is 4 different pacing plans. One for the 184 days of the school year, block schedule spring, and then summer school. So you can see that these lessons can really stretch to 180 days. Or if you're teaching 90 minutes a day, then you've got these longer investigation durations. And then you have the other overview resources, like the cheat sheet we looked at earlier. There's the teacher's edition, so the answer key to everything. That's going to be in the trail guide. Let's go to row. I mean, it's good to have all these links in your resources, but not to the point where you can't find things that you want to share. Teacher guide, teacher edition. Okay, maybe this is the one thing I didn't include. So let me give you a teacher's edition. It's in my slide. All right, click on that link. And this is a 800-page answer key. So don't print this out. Refer to it using keyword search or the table of contents. This was available for a while by the district, but I think it might be too late to get the hard copy. Your admin has to fill out something called a remedy ticket, and then you can get this phone book of a answer key. The good news is Adam and I have segmented this 800-page document into 49 smaller documents according to each bundle of lessons. So you don't need to read cover to cover for this teacher guide, but it is available for an overview. And then there's something called a unit storyline document. So Interactions is written by 8 or 9 different authors. So they all have a different contribution to the curriculum. And this storyline document is in the trail guide, row 16. So everyone go to the trail guide, row 16. And you'll see that if you want another overview, in addition to the cheat sheet, the pacing plan, the teacher's edition, you have these overview documents. And I'll just open unit 1 only because that's what we're covering. But what's nice about this document is that it puts a chart format on all the lessons. Right? So there are 20 lessons and a short description of what the students are supposed to learn within that lesson and the connection and the standards. So storylines, documents can be very helpful. Maybe you want to give this out as a review sheet or a study guide, but of course, maybe make it more student friendly. And that is another overview resource. And then last but not least is the Google Folder Video Library. So this is row 15 in your trail guide. If you go to unit 1, there will be a table that has links to the lessons, GIFs to the hands-on activities. So if you want to put this into a slideshow, then just select the image, go to copy, and then you paste it, and then it'll go wherever you want it to. So let's say I want to put it underneath this slide. See, now I can just use these images whenever I want. And you can too. And you can actually put this into Schoology assignments as well. So this is similar to the storyline document that it shows what students are supposed to learn, but it gives you pictures of the experiments. There's the spheres that we were looking at earlier. And I love that GIFs will loop. They will constantly repeat themselves so that you don't have to click play over and over or rewind the clip. Because there is a YouTube playlist that I made for every bundle of lessons, but that YouTube playlist just goes to the next video automatically. But if you use these GIFs, you can just let it run over and over. I've used these GIFs as warm-up questions, Schoology discussion questions, of course, classroom discussions using your slides, and also whenever I assign a model, I try to include a GIF every now and then so that students can see what's happening. So that's the Google folder library. That's row 15 in your trail guide. And I'll try to be consistent with the wording. All right, 30 minutes to your break time. Let's go into our Unit 1 overview. So what is Unit 1 about? Well, it's about dryers and clothes. Why do clothes stick together when they come out of a dryer? And there are multiple different answers, but students should, by the end of the unit, they should all be able to say with confidence, because of all the activities, that clothes are made of atoms. Atoms are made of electrons, protons, and neutrons. Electrons can transfer between objects. Electrons cause objects to be negatively charged. This negative charge spreads into the air, ionizing the air as an electric field. And then this electric field is what causes the clothes of opposite charges to attract to other clothes of opposite charges. It's an interaction. And that is what we teach. If you lecture this, there's nothing for students to learn anymore for Unit 1. You don't lecture. Here's the trajectory. 5 bundles of lessons where students will experiment with pie pans, Scotch tape, plastic bottles and paper, and then a lot of balloons. So if you were not supplied with all the materials for interactions, your administrator has to fill out something called a remedy ticket and order those supplies. You should get a huge box of supplies. Now, if you're not able to get those supplies, row 12 of the trail guide lists all the materials. And you would have to order those from Amazon or Flynn or from another supplier. If you don't want to give the traditional assessment, which is, I think, 20 questions, it is, and they're open-ended, you can assign a modeling task where they draw a picture. Students attempt to draw the phenomenon of the pie pans repelling off the Van der Graaf by just re-representing the phenomenon, but that doesn't explain what's happening. But then they learn through your discussions and activities and articles and simulations that there are forces that move the pie pan, or at least a direction that the pie pans are moving. And then ultimately you want students to include what's inside the pie pans, not just the arrows. What's between the pie pans, not just pie pans, but electric fields. And then the terminology they can acquire through each activity and discussion. And student models. You want student models to creep in what you're going to teach. Select those things that will help you transition to the next topic. Pi pans are made of atoms. These atoms are made of electrons, protons, and neutrons. The Van de Graaff transfers electrons from the pi pans, and the pi pans become positively charged because of the transferred electrons to the Van de Graaff. An electric field is generated between the pi pans. And I can't read this last part. Here we go. The pi pans repel because two positively charged objects repel when the forces interact in the electric field. All right, we've got about 20 minutes till we take our 10-minute break. I'm going to explain investigation 1. So what should have your first 5 lessons look like? We're in October, so we're going to reflect. Everyone needs to go to row 17, the planning guide 1-1. In this planning guide, there are rows and columns that will demonstrate to you the topics and lessons that will be implemented in your class. So I'm going to put this up here. And then I will put this also on my laptop because I can't read the curtain. So unit driving question. This is a great question to put on your board and just leave it there. Leave it there for 20 lessons. So that could be a month, that could be 3 weeks, that could be 2 weeks. However long unit 1 is going to be for your class. And this will be almost an objective for your students. It's called a driving question, but every time you get someone finishing their work early or someone who says they know everything, they know why it's happening, make them answer this question. And they will forget something. They will not know about electric fields. They will not know about electron transfer. They won't know how to draw it. And that's why they need to stay in the class. Also on the topic of early finishers, because sometimes our classrooms have students that are very, very efficient. This is what I would give them. Go to row 27 in the trail guide, and you'll see a workbook. And this will be for students who finish their work early. These are articles and only articles for these higher level thinking students. And they are to answer the questions in this workbook. But don't have them do it all in one sitting. Just tell them after this particular assignment, go to that slide. After the particular assignment, go to that slide and then repeat that. So it'll occupy the student for at least another 5 to 8 minutes while the rest of the class catches up to that student. During my first year of teaching high school, I had a instructional coach say to me, don't give students more work if they are finishing early, just ask them deeper questions. So that's something you could always have ready for students that finish early. I just don't know what the student does after you ask that question. I mean, do they just ponder it? You could have them draw another model. You could have them write a 2-paragraph explanation. I prefer to just give them a reading task. If any of you have ideas what to give students that finish early, please put it in the chat and share. I would love to hear your ideas. I know Judith is a returning teacher, so is Margarita. So if you have any suggestions for students who finish their work early and are sitting around doing nothing, go ahead and put it in the chat and share with our new interaction teachers. Right, back to the planning guide. So if you are teaching Unit 1, the question has to be asked, why what are some examples of things that stick together and things that don't? So hopefully students have had electrostatic interactions. They won't know to call it that, but they'll know the word static electricity. And they might experience it when they go down a plastic slide or when they rub against styrofoam or a wool sweater. And so the first lesson takes about 20 minutes, and the students they observe the video of the pie pan demonstration. Let's see if I can play that. And this particular setup works really well when you have the small cupcake tins and the small tart tins and the pie pan tins. All three sizes will make a little more engaging demonstration. But you don't have to. You can just do the regular pie pans and have that happen because it's something students can't explain at the moment. Thank you, Judith. So Judith put in a suggestion for early finishers. You had them use a choice board, and then they get to pick what activity they do next. I bet Judith has a library of choice boards ready to go. So great idea, Judith. And Margarita says to have them reflect a concept that they learned in one paragraph. Great idea. And writing skills is probably something all students need more practice on. I remember going to a English teacher PD because my school just had extra spots. And the facilitator said, students don't write poorly because they don't get enough grades on their essays or enough feedback. They write poorly because they don't have enough opportunity to write. So if you want students to be better writers, give them more opportunities to write. You don't have to grade everything because that actually slows down the opportunities. It limits the opportunities you can provide. So I appreciate what Margarita shared. And then Josephine says, have them complete Ed puzzle videos on the same topic. It comes with videos and questions at the end. Great segue to the YouTube interactions channel. Let's go to the YouTube interactions channel because those can be turned into Ed puzzles. Go to row 14, everybody, in the trail guide, and you will see every single let's go to, so you're going to see a different list because I'm the administrator for that. Let me put it over here and put that there. Let's try that again. All right, much cleaner. All right. What you saw earlier were playlists from every single class that I'm teaching, not just interactions. So here is the whole school year of hands-on activities in video recorded format. And these can be turned into Ed puzzles. There is one non-interactions playlist. This is for my physics class, so you can ignore that. But everything else that has a number, that's for the unit. The second number is for the investigation, which is the bundle. And then the third number is the lesson. So if we are going to make Ed puzzles of unit 1, investigation 1, lesson 1, then I would click 111-115 because there's 5 lessons in the first bundle. So I click view playlist, and then we have this. This is actually in my classroom. And then this one. And then the one you just saw earlier. So you could string together a series of these YouTube videos in an Edpuzzle, and then have them answer questions about it. I love Edpuzzle. I think it's not free anymore for unlimited videos in LAUSD. Now I think you're restricted to 10 videos. So you can just post 10 and then not use those anymore and then post 10 new ones. Or you could subscribe or have your school pay for it. Yes. Oh, you're so lucky, Josephine. My school will not pay for it. So I have to pay out of pocket. But the time
I bought it for the whole school.
oh, that's so great.
Mhm.
See, that's when you know your school no realizes the value of technology, or your teachers are all using it enough. Because when I requested it, it was denied. Also lost Nearpod funding. So I no longer have access to Nearpod other than like one megabyte or 10 megabytes at a time, and Edpuzzle as well. So Edpuzzle is $13 a month, and it's monthly. It's not a annual subscription. So you can try it out. You can cancel. They're really good with proration. And the number of Edpuzzle videos already made by teachers is very vast. It's so refreshing to know science teachers will also make Edpuzzles of the same topic in videos. And then you can also use Gizmos. So Margarita suggested Gizmos. Gizmos is free for LAUSD teachers. I actually haven't used it because of the Concord simulations, but Gizmos is also a resource you could use. All right, let's continue Unit 1, Investigation 1. And then we're going to do an assignment for you. You're going to be doing a short assignment of reflection. Okay, Unit 1, Investigation 1, pie pans repelling off a Van der Graaf generator. Students draw their very first models. And a word of advice I have for drawing models in class, especially for students with high anxiety, is tell them to just draw 3 shapes. Okay, just draw me 3 shapes that look like the phenomenon. So for Van der Graaf generator, draw me a circle. For a pie pan, draw me a rectangle. For the neck of the Van der Graaf, draw me another rectangle. Draw me a rectangle, a circle, and a rectangle. They all can do that. And I like to use Google Drawings as a resource to collect the student work. And I will show you that after our break. We're almost there. And then the students will compare models. They'll read an article, what constitutes a scientific model, and they'll do the Scotch tape activity. They'll explore simulations of positive, negative charges, and then explain why the Scotch tape repelled and attracted. Next is the bottle and paper phenomenon. Now, sometimes this doesn't work, and that's when the YouTube channel comes in handy. So please lean heavily on the YouTube channel when the phenomena doesn't work. And the reason why interactions phenomena won't work many times, it's very tragic when it doesn't work, is because of the moisture that's on the surface of your bottles or your balloons or your walls or your rods. Electrons transfer when the surface is transferable, when the surface is not wet. So the drier your weather, the better your phenomena will work. And you can bring a hair dryer and try to improve the conditions. But if you don't generate enough friction between the fur and the object, then there won't be enough electron transfer to produce a charge that attracts. to oppositely charged objects and neutral objects. So, word of advice, please don't be hard on yourself when the phenomena doesn't work for you and your students. It is water molecules that are blocking the interactions. And you'll do the same thing with tape, the same thing with balloons and string and rods. Many, many rods come in the kits. If you don't have the kits, produce the videos. You can actually skip activity 5, in my opinion. All right, so that's investigation 1. The first 5 lessons, those should have already been done. If not, you can revisit those. Let's do our evidence of planning. I need everyone to join this course called the Schoology demonstration course. So go to row 26. And Margarita and Judith, you're already in the class, so welcome back. But the new teachers need to go to the interactions. You go to row 26 in the trail guide, put in that access code, and join me, Judith, and Margarita. So go to courses, go to my courses, join courses. Do not go to groups. Great, we got a request. Let's go here, and I think I put you don't have to get approved, but let's just approve it anyway. All right, let's check our membership. All right, we got Scott, Margarita, and Judith. Still waiting for Josephine and Mina. If you can join us in the Schoology demonstrations course.
Wasn't I think I was there. I saw it on your screen. It said Mina.
Sorry about that. I'm trying to read my curtain. There it is, right there, right underneath Adam. Okay, all right. So these last 10 minutes before the break, your well-earned break is going to be an assignment. Go to October 26th, 2024 PD, click on evidence of reflecting and planning. When you click on that, click on my document, and you will see an assignment for you. IHAM and the Division of Instruction need evidence that you are learning and that you are planning. So for this first session, the 8:30 to 10:15, I would really appreciate it if everybody wrote something you already knew about interactions, something you're going to improve in your classroom, and what your next steps are. And I can check everyone's progress here on this sheet. Great. Thank you, Mina, for filling that out. Scott started. Margarita is going to start. And Judah is going to start. So go ahead and show me evidence of planning. Those who don't do it may get an email from IHAM that you did not do it. So please do it. We're going to do this 3 times. One from 10:05 to 10:15. And then you'll do this again. So don't do the next one early. Just do that before our second break. And then the last 10 minutes of our PD will be the same. Once you're done, you can take your break.
Where do we write the reflection? I'm trying to find where to write it.
So in the Schoology course, there is a, did I close it? Yeah, go to the trail guide. And in row 26, there's a link. Row 26, go to the folder October 26th. And then evidence of reflection and planning. And then click my document, and then you'll see a place for your name, email, school site. And then just do the first row, what I already know, what I can improve, and what my next steps are. So the code for the demonstration course is row 26. Go to row 26 in the trail guide, and then I will
Okay, okay. Let me just go on the trail guide now.
go to trail guide, row 26, and then there should be a request. Join. Yes, once you finish your reflection, you can start your break early. It's a 10-minute break from 10:15 to 10:25. So enjoy this time.
Are we submitting when we're done?
No, there's two more sessions, the
Okay.
10:25, 11:30.
Okay.
But if you're done with the first session reflection, please take an early break. Come back 10:25. All right, everyone, please take a break if you haven't already. If you haven't already started, we're gonna go 10 minutes and we'll stop at 10:25. Right, about 30 seconds left of our break. Right, break time is now over. Our next break is going to be at 11:30. Let's do a quick review of our agenda. So I have here, we're a little bit behind schedule. I'm going to show how to use Google Drawings, then go into investigation 2, investigation 3, and then how to assign and grade CER responses and interactions. And then if that doesn't fit in the next hour, it'll get pushed to the last hour after our 5-minute break at 11:30. All right, so let's go ahead and talk about Google Drawings. So ever since distance learning in 2020, in 2021, hybrid, and then 2022, back in full person, and 2023, full person, and so forth, I have learned to use Google Drawings as a useful tool to assign models, scientific models, but also collect scientific models for grading, for feedback, and also for discussions. Remember, Talk Moves is the major form of instruction. So this is how Google Drawings is to be used in Schoology. So can everyone go to resources in Schoology and click on apps on the left? So resources at the top of your screen, apps on your left, and then you should see Google Drive resource app.
Do we need to submit the one we finished, the assignment?
No, not yet. That one, the assignment that was given at 10:05 a.m. today, that'll be turned in at 12:30 because we're going to add to it session 2 and session 3 reflections. So hang on to it. Don't turn it in. But it'll be automatically saved in case you were worried that it was going to be lost. And if you did submit it by accident, I can unsubmit it just as easily. So how do we get students to draw pictures that explain their thinking? If you go to resources at the top of your page, apps on the left of your page, you will see Google Drive Resource App. And it'll either require you to sign in with your single sign-on, or it's already logged in and you're already connected to Google Drive. So I'll give you a moment to do that. After you connect your Google Drive, go to your Schoology course, your interactions course that you teach. That way you have Google Drive drawings already set up. I'm going to go to our teacher course, the interactions demonstration course, and give you a practice assignment, but you can follow along with your interaction Schoology course. Now that you have Google Drive resource app connected, it's time to prepare the first canvas for your Google, for your scientific model. So everyone go to Trail Guide and click on row 29. It'll say initial model template, row 29.
Sorry, can you go through again how to connect to Google something?
Yes. So did you do the resources button
Yes.
and then apps on the left?
Okay.
Did you click apps?
Yeah, okay, I've seen it.
And then you should see Google Drive, and it'll either say sign in on the right, or it'll just show you some files.
Okay, sign in with.
Yes, click sign in, and then use your single sign-on information.
Yeah.
Now, if you clicked on row 29 of the Trail Guide, you're going to have this template. You have to make a fresh copy of this. So go to File. First of all, make sure you're signed in on your upper right, that it's your LAUSD account, because you want this file to be copied to your LAUSD Google Drive, not your personal. So upper right, make sure it's your single sign-on. Click File, make a copy, and you can either let it say copy of new teachers. I'm just going to put today's date. And now I have a fresh copy. This fresh copy is what you're going to give your students for our scientific model. Now, how do you assign the fresh copy? In your Schoology course, in your interactions class with your students, you're going to click on Add Materials. You're going to click Add Assignment. And then let's call this the PyPans model. And then if it's your student's first time ever drawing a model, then I would have them draw. See if I can get this on my draw 3 shapes that resemble the phenomenon. Label any parts. Later on, they'll learn that parts are called components. And write a 2-sentence description. I'm going to read this blurry curtain of mine. Okay, good. So when you have your instructions posted, click on Google Drive Assignments. And then you will have that fresh copy that you made. Click it. Click Attach. Give it a due date. Give it some points. Give it a category. And then click Create. Now, I'm going to pretend you're my students. I want you all to go to the demonstration course. I think it's in the chat. I'll put the link again. The demonstration course is row 26 in the Trail Guide. The same place we did the reflection. click on that PyPan model assignment. Here, I put the link in the chat for the course. Sorry, I'm having you jump from your students to this teacher version. But when you click on that and you click my document, I will see all the drawings every student is doing from my computer. And then I can give feedback. I can I can monitor their progress if they started or not. So immediately I can click on Miss Afanta's Google Drawing and I can see that she opened it. And if she wants to draw a Van der Graaf and she needs some help, I can say, okay, Miss Afanta, all you got to do is draw a rectangle for the neck of the Van der Graaf, and then you draw a circle for the head of the Van der Graaf, and then draw me a rectangle on top of the Van der Graaf to show the PyPan. Students are going to be very hesitant because they want everything to be perfect. They want to look good in front of their classmates. But on Google Drawings, only you see it and the student. See right here, I could see that Mr. Fonta made a copy of this molecule or this particle moving. Now, you don't have to require them to use everything in the stamp gallery, like right here on the side. But later on, you can, once they learn about molecules and charge and bonds, charge and atoms, right? They'll learn about these eventually. But what I gave you in row 29 of the trail guide, that template is a generic template you can use for every single lesson. Just use it over and over and over. And once you get to a point where students can make even better models than the first one that they made, called a revised model or a final model, then you can input different templates that pretty much use the same idea. But the place to start is the generic template. And then when they're done, they'll click submit. And then if you ever have students that plagiarize one another, go to this little clock in the drawing and it'll show you how long they took to do each part of the drawing and when they did it, right?
Where
So-
do you see the clock?
Oh, so the clock is going to be in,
Oh, on top. I've seen it.
yeah, next to the comments. So you click on. So I've seen students finish models in 3 minutes because they copied everything and they pasted it, or they copy things one shape at a time. And then I've had those students who actually do work at home and they worked on it for a couple hours. And bless their hearts that they will take their time at home to do a classroom assignment they didn't finish and label and describe and draw so that their ideas are compelling and clear. And it's a wonderful thing to see that. And it's also, satisfying to, catch a student who plagiarizes, but way more satisfying to know students authentically do their own work. And they don't have to share this with you because it's already shared. They don't have to write their name on it because their name's already on it. Everything is timestamped and it automatically goes to your gradebook. So if I go to gradebook, I will have PyPan model. Let's see, what are all these things here? Okay, it looks like I have a bunch of other assignments, but right here, PyPan model is where I give the points in the grade book. And evidence of planning, which all of you did. So you all get credit for that. All right, so that is Google Drawings. Let me get us back on track. Close this. And we've done talk moves. We did reflection and plan. All right, so let's do investigation 2. Not investigation 3. Now, investigation 2 is really exciting because it explains what's happening in the air. When pie pans repel or when clothes attract, something in the air has to bring those objects together, and it's invisible. And that's why we have to have students explore it. What are factors that affect the interactions between objects, especially bumblebees and flowers? So let's go to the planning guide. This is going to be the trail guide, row 20. Bring this over to my second monitor. I'll open another copy here, my laptop. All right. So what is the second lesson of the year supposed to look like? Not the second lesson, the lesson 6 through 10. Sorry. Lesson 6 through 10. Well, we need to explain why clothes come out of the dryer eventually, and what are the forces that affect how strongly objects interact with each other. I didn't mention this before, but in the second box, there's an answer key, the teacher guide to all the questions, but it's not the 800 pages. This is the pages for just the lessons 6 through 10. And in fact, investigation 2 is a smaller bundle. It's 6 through 8. 6 through 8. So 3 lessons and all the answers to the questions and descriptions of the lessons will be in the second box here, the teacher guide. All right. So what are the students trying to learn? I am going to open this simulation here on what the students are going to explore and explore it with you. So the students are going to be observing in your classroom a metal triangle that is attracted to a Van der Graaf generator. And that needs to be represented in a simulation as well as a model. Let me show you what I mean. Oh, I keep doing that. All right. In the YouTube channel, it's not the YouTube channel. Let's try this one more time. In investigation 1, it says 1.2. Where's 1.2? There it is. Okay. So students are observing this. Okay, not the commercial. They are observing this. They're not touching Van der Graaf and triangle. Pie pans and Van der Graaf, yes, those were touching. Tapes, those used to be touching, and they touch when they attract. But here, this triangle dangling from a wooden dowel continuously points to a Van der Graaf generator. And students are to explore the possibilities why. What makes anything attract? Like what's happening in the air? So this simulation in the planning guide kind of demonstrates what happens when you record a pointer that is positively charged and the center being positively charged. Notice that the pointer points away from similarly charged objects. If we wanted to make it negative, like the metal triangle in the Van der Graaf, notice that it is pointing towards the oppositely charged object. Now we can do this for days and days, but what the students are doing when they draw this simulation is essentially they're representing something called an electric field. And that is where objects can attract to other objects through the air without making contact. So that's their first exploration of an electric field. Next, in the planning guide, they read an article about it and then answer some questions and then go to lesson 2. Lesson 2 is more simulations where they're going to compare two objects. So they should know what these arrows mean already because of the previous lesson, that it's just the attraction or repulsion between two objects. But now they're going to take two objects and see what happens when they get super close and when they get super far. Just like the Scotch tape, they're going to see that there's attraction when they're closer together, but when they're too close, they repel. And that's when the charges are opposite. Doesn't matter if they're opposite and they're too close. Let me make sure I'm reading this right. Yeah, -1 and +2 are opposites. So they attract until they get too close. Well, wait a second. From the Scotch tape activity, I thought opposite charges will always attract. So it looks like there's some exceptions to the rule. So students can either learn about that from this simulation, or they can just learn that there's something between objects that are attracted that makes them attract. And it has to do with this invisible field. And they can turn it off, turn it on. And notice that most of the pointers between the two objects will point to the other object. They can play a game that also demonstrates the same concept. Let's see if we can get this link open. Work here. It's vertical. There we go. So it's not the most exciting game, but students will still explore the relationship between charged objects, where we don't want it to hit the wall. We actually want it to repel. So if this is a positive particle, we need to make this object A oppositely charged so that it will attract the trajectory of the particle. Okay, it doesn't hit the wall anymore. And what's nice about this simulation is that it sets up success for a future lesson. In a future lesson, in Investigation 4, which is the 4th bundle of lesson plans, the students will know that object trajectories can be altered by different charges. They learned that the electron is a negatively charged particle because it repels a negative plate. And students learn that protons are positively charged because they will collide with the positive nucleus in the middle of gold foil. So even though this looks like a very simple game and students will probably master it very quickly, they will also make a connection that the charge of surrounding objects can cause the deflection of the trajectory. So that's how you succeed at the game here. And the games can get more and more complex as the lessons progress. And then here's one of my favorite articles of interactions. How do bees find flowers? So let's open that up by clicking on the link. Now, you'll find that sometimes your classes don't have time to read the articles. The articles are not essential. The articles are extensions of the activity or enrichment. So earlier in session 1 of today, I had a slideshow that had all the articles back to back for students who finish early. And this is a great article for students to read. They know about bumblebees and they know about flowers, and they know that bees pollinate flowers. Hopefully their elementary school teacher taught them this. If they didn't, then here it is in the article. But that's not the focus. The focus is going to be, how do bees know to go to the right flower and what attracts the bee? You can go as far as it's the smell, it's the hormones or the odors. But when it comes to physical science, students learn that there's an electric field around the bumblebee. When the bumblebee flits its wings through the air, that's friction. It's the same friction in the Van der Graaf. It's the same friction between two pieces of Scotch tape that separate. And it's the same friction between fur and whatever object you're rubbing in the hands-on activities. So the bee becomes charged. And that charge is the opposite of a flower's charge. So without even knowing it, that bumblebee feels an attraction towards the flower based on the opposite charges. I don't know why they're opposite. I don't know why the flower happens to be the exact opposite, but it just is. And that bee knows to hone in on the flower and pollinate. And so that connection also applies to spiders and their spider webs. Why do spiders walk freely above their spider web, but other insects get caught? It's because of the opposite charges between the bug and the spider web. There's another article on dusters, Swiffer dusters. Why do Swiffer dusters pick up more dust than just a feather or a paper towel? Why do Swiffers have a stronger attraction to dust? And it's because of the charge. There's a charge inside of Swiffer dusters, maybe generated from the factory or whatnot, but it's attracted to dust particles. And then the last article that's within this bundle of lessons is the cars. When they're manufactured, it's not wet paint that they spray on cars anymore in the factories. Maybe at home, people use wet spray paint, but in the factories, it's a dry powder that is sprayed on cars. And the charge of the car and the charge of this dry paint is so opposite that the paint sticks. And these applications are what students can identify with. They see cars. Some might even love cars. And the paint that's applied is the oppositely charged object. And so is spider webs and bugs. And so is bees and flowers. So that's pretty much what I want you as participants in this PD to take away from investigation 3. There's a lot of balloon and string hands-on activities. Let's look at the YouTube playlist really quick as a review. So they're going to explore the Van der Graaf and soda cans, balloons hanging from a ceiling, balloons hanging from a desk. Those can be inconsistent because as soon as students tamper accidentally with balloons and rods, it loses its charge. So these videos will be very helpful. And then the Franklin bell is an apparatus that students will revisit how the electric charge transfers to this area between the ball and cans, and the ball and cans interact because the electric field. Now, if you already covered this, then you can just refer back to it in future lessons. But that's investigation 2. Investigation 3 gets a little more interesting than balloons and Van der Graafs, because now you're getting into the chemistry of interactions. Investigation 3 is asking the question, What are all materials made of? Let's go to the planning guide. This is in Trail Guide row 21. All right, there's your driving questions you can write on your board. Here's the answer key for all the questions. And the students observe you cutting paper. Now, what's better than paper? Cookies. If you can get a big soft cookie in your classroom and you put this under your document reader and you ask the students, if I cut this in half, is it still a cookie? You will get their attention. If you ask them, if I cut this in half again, is it still a cookie? And you'll get these students participating. Yes, yes, it is. Yes, it is a cookie. Of course it is. It's just in 4 pieces. Eventually, you keep asking the question, is it still a cookie? And cut it in half again and again until you have crumbs. Let me show you what this looks like. So remember that video library archive where it shows all the GIFs? I believe I have one for the cookie cutting right here. So in activity 131, which is investigation 3, lesson 1. So this is like lesson number 8 or 9. I think it's lesson 9. You cut the cookie until it's crumbs, and you ask them, is this still a cookie? And of course, they're really sad. They wanted the cookie. They wanted to, be a part of the cookie experience. But now it's crumbs. You should expect the students to say it's no longer a cookie. You'll get a few stubborn students that say it's still a cookie. But then you can just send the question back to them and say, if someone gave you a bag of these crumbs and they said they're going to give you a cookie, would you be disappointed? And they would say yes. And then you say, why? Why are you disappointed? And then they would have to confess it's not a cookie anymore. It's just crumbs. And nobody really wants cookie crumbs. They want the cookie. So this premise, if something gets smaller and if something is cut into smaller and smaller pieces, is it still what it originally was earlier? And this is where CER comes in. You ask that claim. What are things made of if you cut them into smaller and smaller pieces? And they can use this cookie activity as evidence. It's no longer what it used to be. Or the next lesson can be evidence that things are not what they appear at the smaller and smaller scale. And that is mixing alcohol and water. So lesson number 10 in the interactions curriculum is to have students mix alcohol and water. Now this has a lot of error. This is very prone to error because when students do this on their own, as the authors of interactions intended, they can mix and get contradicting results with what they're supposed to get. They're supposed to take 5 milliliters of alcohol, 5 milliliters of water, mix it together to get 9 milliliters. But instead, for whatever reason, students are getting 10 milliliters or 11 or 10. That's what I said earlier. 10, 11 milliliters. They're not getting less. Or a few students are getting less. Maybe they're adding more than they should in the beginning, and they accidentally mix 11 milliliters, 6 milliliters with 5 milliliters, or vice versa. So I would implore everyone in this PD to not have students do this portion. Have the students do it. They can observe. They can observe you do it, or our nice little video here will demonstrate it. Let's go to the playlist. Here we go. We are on 1-3, which is right here. All right, so you can play this video of me cutting the cookie. You won't even have to use the GIFs. But this video, 132, shows what either you can do as a teacher or you can just play this video. and that is 25 milliliters of alcohol and 25 milliliters of distilled water make 49 milliliters of mixture. And so if students think that alcohol is just always alcohol and water is always water, then the students should predict that 25 and 25 make 50 because there's just water inside and alcohol inside. But students learn that through this process, there are empty spaces between alcohol and empty spaces in water. And water at the smaller scale is a different size than alcohol at a smaller scale. And this is hard to explain in words for students, but what they will see is that in the simulation of mixing liquids, it is very clear that there will be a different size and different shape for the parts of water and alcohol. So when students start to think of substances made of smaller things that are different than other smaller things, they can make sense of the world. Because when you add these two together and you get less than double, let's say we add our water and we add our ethanol and we shake it up, we're supposed to get double. But the only explanation, other than spilling it by accident or getting it stuck in the original container, the only explanation is that they're different sized particles, and there's different amounts of empty space between the particles that get filled. Now, don't tell the students that. Just let them look at that over and over, and that there is a. Did I make a GIF for this? So my next project is to make a table of contents with a GIF for all the simulations. The last hour of our PD, I will show you how to make GIFs. This is what I use. Let me log in. And you'll see some physics GIFs, but right here, if you can record your screen using Zoom or something called ScreenPal, you can record the simulation moving. And then when you upload that video recording to this website, you can have the animation loop over and over and over. I'm pretty sure I have one of the two mixtures, the two substances mixing. And if I don't, then that's something I need to make. Here's the syringe. Here's the cookie. Okay. So you can see here that this is where you can make simulations of your, you can make GIFs of your simulations. I still need to make one for this alcohol water mixture. Or you can just play it for them. There's also ways to put this into a Schoology assignment. So a great warm-up question is, class, what do you see? What do you wonder? And no wrong answers. They just need to explore this in an assignment. So I'm going to show you really quick how to do that. So let's everyone take this link. This is the mixture simulation. So go to the chat, click on that link, and then click the button share. And then copy that link.
Link number what?
So there's a link in the chat.
Oh,
So click on it and then go to the button share in the upper right. And then copy this link and then go to your interactions course. Not the one with me, the one with your students. You don't have to publish it. You just have to set it up. And let's make it a waterfall question or a Schoology discussion question. So in your Schoology interactions class, go to add materials, click on add discussion. Type, what do you see and wonder? Right? Super easy. Did I typo in this? I did. Darn curtain. Oh, more type. Can't see. Oh no. Let me. Okay, I'm just gonna pull this all to my laptop. This. Okay, what do you see and wonder? Now go to this arrow icon called insert content. What do you see? What do you wonder? Click insert content and then click image media. Now here, go to from the web, click media, and then put the link in there. When you click insert media, you click create. Should be there. Okay, there's one more step. So edit. Go to this little picture icon and then put the link in file URL. There you go. Okay, I'm going to repeat all of that over again. I'm going to delete this. Oh, first let's copy paste this so I don't oh, I need the link as well. Okay, let's just do the whole thing over again. Go to add materials. Go to Schoology discussion. Title it, what do you see and wonder? Click on this insert content button. Click on insert, click on image media. From the web, media, and then paste that link. Insert media, and then one more time. Click on this yellow square. Click on the picture where it says file URL. Double click, paste it one more time. Click insert. I guess you can give it a due date. Enable grade. Just minor details. All activities. Create. Was everyone able to do this? Give me a thumbs up if you're able to do it. One person did it too? Okay. So if you didn't catch it the first or second time, definitely watch the recording over again. You should be able to have a third chance at this and post it. If not, then maybe another time when you are feeling more comfortable with the Schoology functions. But the exact simulation is right here. And if it looks a little warped, then just make it bigger. So it looks like it got kind of squished. So I'm going to click edit. I'm going to grab a corner of this, pull it, and then maybe it'll be more. Yeah. Okay. So you need to stretch the square a little bit so that all the buttons show. So once you got the basics, learn to resize the simulation by dragging that corner. That's going to be too small. It's going to warp the simulation. And then to resize, click edit and pull that open. Now you got yourself a simulation and a discussion question. But you could also put a YouTube video in there the same way we did the simulation, and a GIF, which I will show you after our break coming up. But that is how you can put a simulation into the assignment. And that was for investigation 1, activity 2. All right. Oh, this is my playlist. I'm going to leave this open because we might need it. All right, let's put back the slideshow. Let's go to the planning guide. The syringe activity is also one of my favorite activities because you don't have to buy new supplies. Like balloons, once you use it, they're done. Cookie cut, it's done. But when it comes to even alcohol and water, I mean, you have to dump that out when you make the mixture. But syringes and air, you can use for an unlimited amount of time. Let me show you what I mean. So here, you're going to get students to weigh the mass of air and weigh an empty syringe. So students start to trust the science that even though you can't see something, it's there. Because this is an empty syringe. And when we weigh it, it's going to be lighter than a syringe with air inside. So empty syringe. We stick a nail inside so that the orientation will be the same as a syringe filled with air. So this will be put on. It's probably 30 grams. 39.51. Now, let's release the top of the syringe, let air in. 39.51 is the mass of an empty syringe. Now let's see what happens when air goes inside. 39.58. So 0.07 grams is the mass of air. Students didn't know that. They thought air is weightless. Almost weightless, but it's not. So now they have more evidence. What are things made of, especially at the smaller scale? When you have them do activities like this and the cookie cutting and the alcohol and water, they can do a claim, evidence, and reasoning. So one question could be, can the same piece of paper be cut indefinitely, or the cookie be cut indefinitely? Students will say things like, I guess you can cut them, but you're not going to get very far because they know about molecules already. Or students will say that paper is something you write on or fold. You can't do that to something that you cut. Okay, that's pretty good reasoning. If you cut paper into smaller pieces, it's no longer paper. Okay. They observe the alcohol and water mixture experiment, and now they have evidence. If something gets really small, is it no longer what it used to be? And they'll explore the simulation. They'll observe the syringe activity. And they could do alternate activities where they weigh a balloon versus an empty balloon. And now they have evidence for their CER. So I've had students write a claim and then they revise their claim based on evidence. And some students will say, oh, the evidence is all these experiments. Well, that's not good evidence. That's just saying a vague statement. But what is a good piece of evidence is when a student says something like this. After the activities we have done, I still believe that paper is still paper regardless of size until the different elements that make up the paper are separated. I still agree with this because it is similar to the particle model of matter, which I think was the best representation of things and experiments we have done regarding matter, like liquids and gases. So the student is referring to the experiments we've done, such as liquids and gases, a little bit better than the first student. And then we have this. I would say that eventually, if you cut paper enough, it could not be identified as paper because there are certain characteristics that pertain in order for it to be considered paper. I could use the evidence previously stated about water and ethanol mixing and the air particles in the syringe to properly explain my thinking. Okay, well said. This is probably one of my top students from a few years ago. But he or she is citing the evidence. So when you get students to write claims, let them know it's not going to be the only claim they write. Let them revise it either after each activity or after several activities. And then either assign the same prompt or a similar prompt. Like if all students start saying paper is still paper, then ask them, is water and alcohol made of the same things? And now they're thinking, oh, things are made of smaller things that are not the same small things as other small things, like water and alcohol particle. Is air made of nothing? Here's a good prompt that gets students choosing a side. Yes, it's made of nothing. Oh, but then why did it weigh 0.08 grams? Oh, it's made of something. Okay. Well, now they can start revising their thinking by using a claim, a question, or a follow-up question where they can explain their thinking. So this is 3 templates you can use for claim evidence reasoning. Let me go to that. I'll just put all 3 in the chat, and you can go through each one at a time. So this first one is something I created. This makes claim evidence reasoning easy for you to grade, but also for students to follow. Tell them, okay, just do rows 1 through 3 today. Don't worry about rows 4 and 5. Or early finishers. Now that you've done rows 1 through 3, please do 4 and 5. And these sentence starters or these suggestions or these hints will guide the student's thinking and make it worth 5 points. Template 2 is something made from my colleagues where the student puts, what's the big question? Why do clothes stick together when they come out of the dryer? What's some science background? Opposite charges attract, similar charges repel. Electric fields cause objects to interact, whether they're closer together, they will attract more strongly or farther apart. They'll attract weakly. What's the claim? So they'll try to answer the big question, and then they can organize evidence in columns and explain it. And then last but not least is this very robust template where they actually put together 3 different paragraphs using this table. And it would be worth 12 points. So those are some resources for you to, explore and try out, pilot and field test in your class. And if it is not for you, it's not for you. If it's not for your students, at least you tried. You tried to see what's out there. Remember, you're trying to win over your students. If it connects, if it gets them to go back to their seats and to start their assignment and to get off their phones, then you have done your job, right? All right, it's time to reflect and take a break. So everyone go to the Schoology demonstration course and go to the October 26th folder. You have 10 minutes to add more to the document. Now we're doing the 1025 through 1125 row. What's something you already knew about investigation 2 and 3? what's something you can improve about investigation 2 and 3, and what's your next steps for investigation 2 and 3. The rows should not be identical in the screen section because we cover different topics. Please take 10 minutes and then take a 5-minute break after. When you finish your reflection, you can take your break early. Our next break is 5 minutes. So we will reconvene at 11:35. Thank you for reflecting. All right, everyone. Now, please take a 5-minute break if you haven't started. See you back at 11:36. About 15 seconds left of our break. All right, everybody, welcome back. Let's get into our final stretch of the day. Investigation 4, 5, how to make GIFs, and one last reflection, and then we'll be done. So investigation 4, what are nature's building blocks? Let's open up the planning guide to the next investigation. So this is trail guide, row 22. So this is when interactions gets very specific. Students learn that parts of objects at the smallest scale are different than the smallest parts of objects of other objects' smallest scale. And they don't know what they're called yet. And they're going to learn that in investigation 4, the name is atoms. And atoms are made of electrons and protons. Now, don't tell them that. Instead, give them the opportunity to figure it out. And this is what's going to happen. You have to make a box with holes in it. 16 holes to be exact. And in this box with 16 holes, you're going to put an object inside that will cause a laser beam to either pass through completely or deflect. So this is one image you could use for the box. Let's go right here. Looks like there's more than 16, but you can do 25 if you want. That just means more hole punching for you. Now the end of this box is going to be removed. And this side of the box is where you shine a laser through each hole. And each box, each hole correlates with a letter and number. So you can call it, row 1, 2, 3, 4, 5, 6, letter A, B, C, D, E, F, G. And then you just tell the students which coordinate you're shining the laser through. Now, I like doing this activity in investigation 4 because it gets students curious, first of all, what's in the box. There's just something psychological about not knowing what's in a box, and you need to find out what it is. Maybe that's why Christmas is so exciting, or your birthday. It's like, what's in the box? And I have my most, active class in my career right now. And I'm able to get the class to actually focus because they all want to know. Every single student, 30 students, they all want to know what is in this box. And they ask, they blurt out questions. Is it from this classroom? Have we seen it? Can I touch it? Of course, they want to touch it, but the parameters you set for this activity is this object is from the classroom. It fits inside this box. You cannot shake the box. You cannot touch what's inside. Instead, how can you make a good guess by shining a laser through these 16 holes? And they're okay with that. They don't fight that. They think they can do it. They think they can guess what's in the box. So you have them either use a Google drawing to record what's in when the laser is blocked or deflected or passes through, or you can use a piece of paper that has a chart on it. I like to guide the students and say, if the laser goes through, it's a circle symbol on your paper. If the laser gets blocked, it's an X. And if the laser gets scattered or deflected, it's a slash. In other words, half an X. And so the students, they say, okay, let's do it. You got to move the students from the front of the classroom towards the back and then you put this box on a cart, and then you shine the laser one at a time through the holes. This year I used hand sanitizer, the pump. I like the hand sanitizer pump because it's skinny, so many of the lasers pass through. But when the lasers do hit the bottle, when it hits the label, it'll block the laser completely. But when it hits the portion not covered by the laser, it becomes a blur. So the students are fascinated that something inside the box would cause a blur. And then the neck portion of the pump blocks the laser, and so does the spigot of the pump. But it blocks it as a T shape or an L or a 7, the shape of a 7. So now you have students dying to know what's in this box that makes lasers blocked or scatter, and it's the shape of a 7. Now that I told you what's in there, you probably can instantly connect. Okay, that's going to be so obvious. But when students don't know that it's a hand sanitizer, they get so excited and they think they can beg the information out of you. You have to hold strong, because the benefits of them not knowing is that they will stay curious. They will stay curious, and they will know what scientists felt like when they shined lasers through glass tubes, when they shined alpha particles through gold foil, when they would weigh the mass of helium and they didn't know about neutrons. There's so much unknown in science that students get a good taste of it in this mystery box activity. And so I highly recommend doing this. Once you make the box, just use the same box every year, and just store it in the corner. And then once the students take a couple good guesses, have them use their skills of deductive reasoning. What is something that would make lasers blurry? Is it something that is completely solid and dense, or is it something that is opaque or translucent? So they can start connecting. Oh, it's not metal. That's a metal object. There's something clear. It's glass. It's something made of glass. Or it's plastic. It's made of plastic. Something that helps them make connections based on the evidence is what you're doing with these students. And they can use these skills outside the classroom, but especially in investigation 4, where they learn about electrons and protons. At the end of the activity, do not tell them what's inside, because you're kind of holding their minds captive. And the longer you can do that, the more they will be engaged. So one participant in this meeting said, how do I keep my students engaged? You have to keep them curious. So I tell my students, if you remind me at the end of the year that you want to know what's in the box, I'll tell you. And they'll moan and they'll groan, but they will actually love it. They will love that you are not giving it away. And some students, they remember, and I tell them. Other students, they forget to ask, and they will never know. But what they will know is it was something that was translucent. It was something transparent. It was something that was narrow enough to fit in the box and not block all the holes. And it was something that is not typical. It was atypical because it had that 7 shape. And so you can use whatever you want inside the box. And I actually dare you to be very creative. And when the students try to guess, you're gonna have them engaged. You're gonna hold their hearts and minds captive. And this transitions nicely to the discovery of the electron. So if you have a green laser, or if you're able to acquire one, then it'll match the color of the simulation in the activity, which is the cathode ray. So if this will respond. There we go. Okay, that's a timeline. Let's get to my cathode ray. There we go. So these are all articles. There we go. Cathode ray. Okay, so students are going to see, okay, it's not a box, but it's a glass tube. And this laser can bend, just like the laser when it's scattered in the box. And the laser can be attracted to the positive plate, or it can be attracted to the negative plate, or repelled by the negative plate. So students will use the same reasoning that they did with the box, similar reasoning to the questions in the activity, where they analyze this experiment done by actual scientists hundreds of years ago. And if they can deduce that this laser coming out of metal, out of a battery, is negatively charged, then they can connect the electron to it because it's attracted to this positive plate and it repels this negative plate. They learn from the Scotch tape activity. Scotch tape with the same charge is going to repel, and Scotch tape of opposite charges will attract. Pi pans in the Van de Graaff with the same charge will repel, and objects that are attracted will come together, like the balloon and the wall. That's an experiment you do in investigation 1. And the bottle and the paper, and the bottle and your hand, and some of the rods and balloons. And if you want to do additional activities, I do this. I do a balloon with pepper. A charged balloon will attract pepper off a plate, and so will a balloon and a soda can knocked on its side. I have GIFs of this in the table of contents. Let's see. So this is the wall and balloon. If you get for watching this. I guess it didn't save there. Oh, the YouTube channel shows it. You go to my YouTube channel. Didn't know I closed it. Okay, bear with me. YouTube, it's back. So when you get to investigation 4 for unit 1, you've got this phenomena. Here's a video recording of a mystery box by Adam. Marker board, cathode ray tube. Let's do 1.5. Right here. Right here. So once you start to exhaust the activities and interactions, you can start looking up online some other activities that do the similar phenomenon. So here's one of a soda can and a charged balloon. So right now they're both neutral. But then once you charge the balloon with a microfiber towel, it will attract the soda can. And it works best with a small soda can, not the big ones, the little 6-ounce ones. And the balloon and a microfiber towel works well, as long as the microfiber towel is not mixed with a dryer sheet in the dryer, because that coats the microfiber towel, so it's slippery. So you want as much friction as you can with a towel and a balloon. So put it in the dryer without the dryer sheets. Here's a pepper and a balloon, right? Right now they're both neutral. But look at this. The pepper rises through that electric field and attracts to the balloon. And it makes like this very engaging sound of the pepper ramming into the balloon. And so that is another piece of evidence that opposite charges attract. A third experiment is balancing a straw on a Gatorade bottle, and you charge the balloon, and you can make the straw repel. And you ask them, why did they repel? And they can tell you with full confidence it's the similar charges. And then try to make that connection. Okay, the similar charges between the negative plate and the negative laser is why they repel. And in the lesson, students learn that this negative charge is called the electron. And so now they have the vocabulary to include in their PyPan models that electrons are inside of atoms, and atoms make up all things. But as soon as objects have a lot of electrons, or if they have more electrons than other parts, such as a proton, it's going to be overall negative. And that overall negative object can repel another overall negative object. So that is the value of activity 3 in interactions. Activity 4 is discovering the proton. Now, this activity could be a little more difficult because there isn't like an engaging mystery box, but there is an image that the students can refer to and a simulation. So in interactions, there is an image of the cathode ray experiment. Let me show that to you. Let's go to my chemistry slide deck. So I'm gonna go to a slide deck in row 30, and it's the second link in row 30. And there are these images that I was able to find for Rutherford's experiment. All right. So in the trail guide, row 30, the second link, I'm on slide 20. And interactions doesn't give you this GIF here. This GIF is important because it lets students visualize that the gold foil experiment is made of particles. And students, they don't see that in interactions questions. They see that it's a laser also, or just a trajectory. So once you get this GIF in front of them, whether it's a warm-up question or a Schoology discussion like I showed you earlier, the students can now connect that, okay, these particles, they deflect every once in a while, and every once in a while they go backwards. Now I understand this picture. 1 out of 10,000 bounced back, and most of the particles went straight or turned a little bit. And kind of like the mystery box where the students are trying to guess what's in the middle of an atom because they can't see it, and so are the scientists. But this simulation in activity 4 makes it very clear, if this was the atom, all the particles go straight through. Not a single one will get deflected until students figure out that they can shrink the positive center of an atom and then shoot the alpha particles. And now many particles go through, except for the ones that hit the middle of the atom. And sometimes it's deflected backwards, sometimes sideways, sometimes diagonal. But most of the time, the particles go through. And so this is a simulation that students can explore to make a connection that atoms have a positive center. And they learn that the positive center is the proton. And that's activity 4 inside of investigation 4. The last lesson in investigation 4 is where are the electrons? So this is an activity you could do in person, but also show a video of. I've done it in person. Students, they fairly enjoy it. All you do is draw a circle on a piece of paper with an X through it, and it becomes a bullseye for them to drop their pencil onto. You have the students drop their pencils or pens on this bullseye on the floor about 20 times. And what happens is they get this result here. Where is it? Right here. This marker. I'm going to put this in the slideshow to zoom it in. Put it right here. So in activity 4 of investigation 4, they take a pencil or a pen and then they drop it on this target as many times as possible. And then you ask them, what pattern do you see of where these markers and pens are landing? What's the pattern? And they'll tell you, oh, it's towards the middle. And you say, okay, well, if things are attracted towards the middle of a target, then you can most likely guess where the next marking is going to be. And they say, oh, it's in the middle. And you say, how do you know? And they say, oh, because that's where it usually landed. You go, oh, okay. So then in the simulation, students see that it's the same thing with the electron. When the electron is, oh, this is a dartboard. When the students see the electron traced on an atom, they notice that most of the last locations of the electron is near the nucleus or the proton. I wouldn't even use the word nucleus, not yet. The closest location, the highest probability of the electron's location is near the protons. You can ask them why, and they might not know right away, but then you can say, well, what would attract a negative particle? They should know by now it's positive. And you say, okay, well, then why is the electron in this simulation hanging out mostly around the proton? And then they should be able to say it's positive. And you could say, oh, and then you could even press them further and say, well, why would a positive and a negative attract? And then they'll say, oh, because of the Scotch tape activity, or the balloon in the wall activity, or the balloon and pepper, or the balloon and soda can, or the bottle and the paper. Opposite charges attract, just like this proton and electron. But the electron's moving so fast, it doesn't stay with the proton. It actually keeps moving out and rotates around. And you could tell them that is still a mystery. Why doesn't the electron and proton stick together as one piece? It just keeps rotating and rotating and orbiting and orbiting. And that is when students learn that atoms are made of clouds of electrons, not just hard parts of electrons and protons. And that's investigation 4. So at this point in time, students should be able to articulate that all things are made of atoms. Atoms are made of protons and electrons. And electrons are negative, protons are positive, and opposite charges attract, and that's why the atom stays together. But since the electron is constantly moving, it's more of a cloud than a single unit. or one piece collided together. And that's investigation 4. Investigation 5 is about neutral objects and charged objects attracting. So let's close this and this. And now we're here. Let's go to the planning guide for investigation 5. We have 29 minutes left. You made it. You're so close. Go to planning guide, go to the trail guide row 23. And let's look at the periodic table. Now, they might not know about the periodic table because you're their first physical science teacher. Maybe they've heard of it before. For now, you can just show them the periodic table and tell them that the periodic table shows how many protons each element has. And that'll be the connection. In the first activity, there is a worksheet where you're going to analyze what effect do protons and electrons have on the identity of the atom. So for example, we've got this simulation and it says atom, it's called the atom builder, atom ion builder. So you can put this into a Schoology assignment and have the students complete the questions about it. I'm finally understanding what Scott was referring to when it was 1.1.1, 1.1.2, 1.1.3. Like those aren't assessments. Those are the lessons or activities the students need to complete. And when they do complete it, I recommend not grading every single question. I recommend that the student, that you as a teacher grade the last 2 questions. And then in the grade book, just give them 4 out of 4 points, 3 out of 4 points, 2 out of 4, 1 out of 4, based on how much they completed. So let me show you what I mean. Simulations like this are supposed to be part of an activity in Schoology. So if you're a new teacher, in the interaction teacher group, there is a tab called resources, and how to add interactions to a Schoology course. And then you have some options here. Blended instruction, or what does that one at the bottom say? In-person or blended instruction. So that is what we're going to click on. And then here you have several options. Now, the Nearpod versions of all the Schoology activities are going to be dependent on your school paying for Nearpod. It's $160 now per year. You could try using the free version, but you're forced to delete anything over 10 megabytes. And that is very few slideshows. So you can either go through the process of deleting every Nearpod you make or use, or not use Nearpod, at least in the meantime. And then there's this option here, the quiz format, the test quiz format. I actually recommend this. I think Adam recommends option 1 because it's a lot more interactive. Option 3 is what I recommend because my interactions with the students are the discussions and the model building on Schoology. These activities in option 3 is more self-paced. So let's go to investigation 5. and activity 151. And so you'll see the questions that the students have to answer and the simulations embedded. And notice that they're all open-ended responses, just like the assessments. So what I would do to save time on grading and to get a good snapshot is to grade the questions that are the most robust. So let me pull this over so I can read it. Yeah, like question 13 says, explain the evidence that supports your claim. And then the question 12 is asking you to make a claim. What would happen to materials if they became charged by transferring protons? So students are going to be forming their explanation based on the simulation, but also past evidence. So I would grade those questions, and everything else you can just consider a scaffold to get to these last two questions. And if you run out of time to even grade activity 151, you can just grade 152 because that builds upon 151. I wouldn't go too far and skip grading 3 or 4 activities before you start grading, because you do need to hold your students accountable and need to make sure that they're not putting IDK or not sure for every answer. And if they do, then you're gonna have to call them out on it. You'll have to talk to them one-on-one. But once you let students know the first time that IDK and I don't know and not sure, no idea, answers like that are unacceptable, it usually stops because you stop giving points to those types of answers. And I would try to stick to a 4-point scale. 4 meaning they completed it with accuracy. 3, it's partially completed with accuracy. A 2 if they attempted it and they did half at least. And then 1 is if they didn't do it at all, or they put in very little effort. All right, something's in the chat. Yes, those, or what I was referring to, I think my colleague used them because some activities are going to be conducted during class. Yes. So another benefit Scott and his colleague bring up is these activities in option 3, they all have the videos already embedded. It was meant for distance learning, but you can still use distance learning resources for in-person instruction. Option 1 does a little bit more in-person interaction in terms of experiments. Like the videos are not embedded in the questions from what I remember, but in option 3, the videos are. So assign these if you want to have the videos attached. Okay, so investigation 5 is about the identity of an element now that protons and electrons are discovered, and properties of the atom changes when the atom gains or loses protons. And then we get to an activity where you stick a balloon to a wall. Now, this was done earlier in investigation 1, but you're going to bring it back in investigation 5. And this only works in the most dry weather. So let's look at it from a full video perspective after that commercial. All right, so you get a neutral balloon and a neutral wall. You show the students that they do not attract, they do not repel. They're both neutral. Once it's very clear to them that the balloon is not charged, you charge the balloon and you get a new interaction. And that is a charged object with a neutral object. Try to use a yellow balloon because the simulation that follows this is a yellow balloon. Just one less thing to for the students to figure out. So this works on most walls. I've seen it work on whiteboards. I've seen it work on cabinet doors, but for me, walls that are very dry work best. So that's the phenomenon students are trying to figure out in investigation 5. And there is this really good simulation of the balloon. See if I can get this working. Not this one. This one. So just like a yellow balloon that was in my hand, we have a yellow balloon in this simulation. Students can immediately make the connection. Now, what's really powerful about this simulation is that you can click show atoms, and then you can make the balloon negative, or you can make the balloon positive when that fur was rubbed on the balloon. So when you get students to observe what you just did is now shown as a simulation, they can actually see that, oh, look, if the balloon's negative, something happens inside the wall. But if the balloon's positive, a totally different interaction happens. Like you ask the students and you have them, answer questions in the Schoology assignment. What's moving away from the balloon when it's positive or negative? And if they look at the key up here, it's the electron. And you ask them, why would a negative balloon push away electrons in the wall? And by now they should know similar charges repel. And then you can say, well, why doesn't the balloon push away completely? Why is it only the electrons that push away? And the students could figure out that the proton in the wall still attracts the opposite charge. And so everything that you've been preparing the students for comes to fruition here. Everything's made of atoms. Atoms are made of electrons and protons. Electrons are negative, protons are positive. And when a negative object is near a proton, they'll attract. Or if a balloon is positive, the electrons in the wall will attract. And so it explains the phenomenon that you just did. You could have your students try it too, if you have enough balloons and if you have a small enough class and enough wall space. And it works on the driest days. And if it doesn't, show them this video. So now we come to the end of our investigation 5. Why do pie pans repel off a Van der Graaf generator? And I found that when students see that charged objects are charged because electrons transfer over, they can use that in the explanation of the pie pans. If you've ever done skits before in a class, you can do that with interactions as well. And it's only one skit. Let me find my YouTube window. Okay, let me open it again. This is row YouTube video, row 14. Okay, I'm gonna put this in incognito mode. Paste. So we are in investigation 5. Neutral object. Okay. So the Franklin bell is something that was in investigation 2, right? It's that ball that rattles between 2 soda cans. Students learn that only when the Van der Graaf is plugged in does this ball rattle back and forth. And that's because of the electric field. But if you get students to do a skit that represents each part of this experiment, they will see even more clearly why the ball bounces back and forth. So check this out. This was in 2017. I get 4 students to come to the front of the class. I hand them each a positive and negative charge because they're all going to be neutral. Van der Graaf, soda can, pith ball, soda can. When the Van der Graaf is turned on, look what's passing between the students. I ask my classes when I show this video, what's being passed? And they say, oh, a negative. When I ask them, okay, what's the negative called in atoms? And they say, well, it's an electron. So when this electron gets passed from Van der Graaf to can, from can to ball, ball to can, notice what the ball does. The ball will interact with this double negative and this single negative and then repel. So let's wait for that repulsion. I'm like explaining to them in real time. Okay, so once they get the hang of the process, they're going to do this continuously. But it's really important for students to see how big these positives and negatives are. So you see, she finally did her repulsion. Okay, now we have the charge being passed down after they're done laughing. All right, so plug in the Van der Graaf and the electrons being passed down. The ball is repelling the can, passing the electron, and then bouncing back. And that repeats over and over and over until students start to see, oh, electrons can be transferred. They don't just stay where they're at. They can be delocalized and they can cause an electric field to force attraction and repulsion between 2 objects. So you can have students draw a model of the Franklin Bell, but I find that time is better used to have them draw the pie pan and how the Van der Graaf transfers electrons to the pie pans to the point where there's an electric field in the air and the pie pans become positively charged, repelling one another. So that's how interactions get students to explain phenomena from this point in time. Let me show you. Right? They think pie pans they think of the phenomenon as this first. And then they grow to learn that, okay, something is forcing pie pans away from each other. But ultimately, after 20 lessons, 20 activities, many hands-on activities, claim evidence reasoning that it's all coming down to the neutral objects becoming charged, repelling one another. And that's unit 1. All right, everybody. Let's do our reflection and call it a day. Go to Schoology and reflect on your observations, your prior knowledge, your plan for the next couple months. Go to October 26th and do your last reflection of the day. We'll set a timer for us.
Hi, Michael. What are we doing now?
Oh, on my screen, it says time to reflect and plan. 10
Okay, to plan our lessons.
No, this is the reflection assignment in Schoology, the demonstrations course.
Okay, okay,
And
thank
then click submit when you're done, everyone.
okay.
And I would like for you to sign out at 12:30. That's going to be in row 30 of the trail guide. Phenomena being analyzed. We didn't get to do the GIF part of the PD, so I'm gonna put a video recording of how to make GIFs from a previous PD. GIFs are those images that are looping the experiment over and over and over again. All right, everybody. I put the link to the sign out sheet in the chat. You may log off now. I'll see you in February for hands-on activities at Eagle Rock. Adam will be meeting you at Eagle Rock in January. So our next PD is in January. Thank you for being here. Make sure you sign out at 12:30 exactly. But you're dismissed. You may go. Enjoy your weekend.
Do we have a PD in November?
I'll check the calendar again. I didn't see one.
I don't
You're
remember
right.
this.
You're right. There's November 18th. I apologize. It's going to be on Zoom, and half of it is UCLA Center X presentation.
It's a Zoom session?
It's a Zoom session.
Okay, good. Thank you, Michael.
Thank you.
I really appreciate it. I always enjoy your trainings. You're awesome.
Oh, thank you, Margarita. I always enjoy you being here and contributing your wisdom.
No problem. My pleasure.